Morning, everyone. Buenos días. Are you ready to start? I don't. You are. That's good. Some of your friends and colleagues probably are not yet, but I hope they will come in a couple of minutes. Is it while we are getting ready? The question is it okay? Everything was okay with yesterday's content. The tutorial is online. Upstalling is working. Yes. Okay. So on the second day, we finally set up the system. Okay. So what do you think? You see this one. Who is the guy on the camera or the lady? Who is working with the camera? Could you please adjust so that we see both the parts? Yes?
We're seeing both the boards.
Can we see ourselves here for a moment to make sure that we're... Absolutely. Thank you very much. So, okay, now let's start. And today's lecture will be divide and well, I have revised the plan that I have made for that. I think it's about a one semester course, but we will try to squeeze it in our 2.5 hour class record. So as usual, as we did yesterday already, and as we more or less did today. So, what is the main idea of divide and conquer algorithm? The main idea is that you have your data that you want to process, and it's easy to process the data if it only has a kind of size of, say, 1. So one piece, one chunk of data, one element is easy to process. But if you have the data, you would like to maybe do some partial processing. There are two main approaches, well, maybe three main approaches, when you know to process small data and you have to process big data. One is well known to us dynamic programming, when you make gradual increases to your data and updating your solutions using some formulas. We will get back to dynamic programming on the next lecture on Friday, and that will be more of advanced techniques. The other one may be like similar to dynamic programming, the greedy algorithm. And the third one that we are going to discuss today is divide and conquer. The main difference is that, unlike dynamic programming, when you have, again, small increases in your problem, in divide and conquer, you do like this. You have the data, you split it into usually two, maybe in some cases, some a little more parts. We will see that, for example, today as well. Then you process the two parts separately. This is called the divide step. And then, after you have calculated some results of the parts of your data, you combine them to get the solution for your whole data, which is called the conquest. So divide. Then you usually use the same or similar algorithm to process the halves of your data. They are usually divided on and so forth. And then, after processing, like this, you conquer to get back to your original data. Well, the best known probably divide and conquer algorithm is merge sort. That everybody heard about merge sort. Where today we will see the algorithm which is absolutely the same as merge sort, but for some reason merge sort is called the basic algorithm, like everybody studies it on, like, I don't know, third or fourth class of your algorithm data structures course. But the second algorithm that we're going to say today, which is fast Fourier transformation, is called one of the most advanced algorithms. Although, as you will look, if you will look closely, It is absolutely the same. You can just copy paste, make some 2 or 3 changes, and you will get the 50. That's very easy, actually. But it has, for some reason, the feeling that it is difficult. We will fix that today. But then, another situation when you might like divide and to organize divide and conquer is the problem on the trees. In case of the trees, there is again classical approach which is called dynamic of the tree. When you take your tree, solve the problem for subtrees, and combine them, thus moving up the information about the solution. That is dynamic programming on the tree. But sometimes, especially when the information is passed in many directions, like from this there, there, dynamic programming is not the suitable way to solve. And you might also like to make kind of divide and conquer algorithm for the trees, which means that you take some vertex like this. You don't have the fixed root, you choose some vertex to be the root. Then you solve the problems for the subtrees and combine it together all together. The problem usually is which vertex should we select as the root. And the solution that we will discuss today is so-called centroid of the tree, which is the vertex such that no subtree has more than half of the vertices on the subtree. It will be not so difficult to see for us that there is at most, there are at most 2 such vertices, any of them with reduction. And after that, if we do the same for the subtrees and so on, we will see that we can build over our tree, we can build the alternative tree view called the centroid decomposition of the tree, which can be used to solve some problems that are not approachable with dynamic programming, but will be approachable by which sometimes is called, and I agree that it is similar, a dynamic divide and conquer on the tree. So that is our wild plan for today. Divide and conquer arrays-like data, and divide and conquer trees. We will probably, as yesterday, unfortunately, the surface automaton that I was planning to at least sketch did not squeeze in into our lecture. Same thing can happen with something today. Let's see how it goes. Let's start with divide and conquer on arrays. Okay, so how does merge sort work? Let's start with merge sort because it's a canonical example. And again, fast Fourier is just the same idea. So let's try this idea on the simple one. So you want to sort the array. What you do? The divide step actually the divide step is in most algorithms is very easy. You just go to the house and that's it. It's not always the case. The alternative algorithm that is also divide and conquer, called the quicksort. Have you heard about that? Quicksort. Or sort. Well, it goes another way. Third, its divide step is difficult, and this difficult is the wrong word. More difficult, a little bit more tricky. And its conquer step is a little easier. Just nothing. But in most divide and conquer algorithms, it's divide step that is easy. Okay, we just go to the hubs. So we take these 2 hubs, and the recursion sort them. If the recursion goes down so that there is only one element, it's of course very easy to sort it, but because one element is automatically sorted. So now, up to this part, you have 2 sorted arrays, and what you do, the conquer step, you are using 2 pointers method, so you go by 2 pointers. here, and the new array which is going to contain the sorted version of the original array. This procedure is called merge sometimes, and if I remember correctly, in C++ and library it's called merge. You pick the smaller of the pointed elements and put it into the resulting array, and you move that pointer to the next element. And when one of the halves is empty, the other part just goes to the resulting array as it's. So this is merge sort. Everybody knows merge sort, just to make sure that I don't need you more details, yeah? Okay. So looking at merge sort, what is its time complexity? Let's see. So when you're working with any recursive algorithm, especially with a recursive algorithm of this type, like divide and conquer, it's usually you would usually write down the formula for a recursive formula for the time complexity. So here, the time complexity to sort the array of length n, that's denoted as T of n. What is that? Well, divide is free, mostly. Then we sort two arrays of size n divided by 2. And then we merge. The merge looks like it takes linear time, so you just pass the two arrays with the 2 pointers, so it's linear time. So this kind of recurrence can be generalized to be like this: T of n is A times T of n divided by b. Our case plus of n to the power of c. So this type of formula, it usually occurs when we are considering recursive algorithms of divide and conquer type. And let's find out how long does it take in general. That there is a formula, the general formula that covers the general case. It's called master theorem, and it's usually taught in algorithm data structures courses. Let's see what the idea behind that. Let's draw the tree of recursion. So the top level, oops, azul, quadro branco, super long origin distance. I mean, okay, we can. So the top level of the tree, we have that n to the power of c. So then we divide it into a parts. And each part has like n divided by b to the power of c. Yeah? Then each of those is again divided into a parts, and so on. So there are actually 3 main options. Let's see what is the total complexity of the corresponding level of this string. So as you can see, here we have n to the power of c. Here we have a times n to the power of c divided by b to the power of c. Yeah? Here we would have a squared times n to the power of c divided by b to the power of 2c, and so on. Okay? So it's clear that the corresponding level of the tree has a divided by b to the power of c to the power of the level number L. So there are this, and this is multiplied by n to the power of c. Doesn't matter because n to the power of c is always the same. So this is actually the geometric progression. So there are 2 options. The first element is dominating if this is smaller than 1. the last element is dominating and is greater than 1. Or they are all the same, if this is exactly 1. So we say that if a divided by a to the power c less than 1, then this geometric progression sums up to something proportional to the first to some constant. And the complexity is n to the power of c. If a divided by b to the power of c is greater than 1, then it's exponentially growing, and the sum of the exponentially growing sequence, geometric sequence, is proportional to its last element. So it's like how many elements you have, like I guess logarithm of a, logarithm of a of n. See? Logarithm
of base b.
with the base a, I think by b. Right? Because it's by b. Yes, by b of n. That's the number of levels, and we will have a divided by b to the power of c to the s power. It can be simplified, it doesn't. And if it's equal to 1, then all the levels are the same. How many levels are there? There are this number of levels, and they are all the same. So the total complexity is n times logarithm n. The basis of the logarithm is not important in this case, it's constant. So that is Master's theorem. It's more or less primitive version. And our case, let's see. A is 2, B is 2, and C is 1. So 2 divided by 2 to the power of 1 is exactly 1. And this is the last case. So our plan complexity is n over. So from the practical point of view on the contest, if you have created some recursive solution, what you take a look, you take a look at this fraction, and if it's less or equal to 1, it's usually okay. Question?
Does the power of c disappear?
Oh, yes, the power of c didn't disappear because it's usual. It's also, yes, here it's not. Of course it did. So, if it's less or equal to 1, it's usually okay. And if it's greater than 1, it's usually not okay. Exponentially growing time complexity. So you see that n here is in the power, so we get something. Of course, it's not a logarithm. After transformation, you will get something, but usually it's not okay. So you must think about that twice again. Well, so now that we have set up the main theory kind of approach where did you go, let's consider some examples of the problems. I will give 4 before going to the global f of t algorithm that has a special value by itself. I think that we would consider 4 more specific algorithms that don't have such a wide generalization as such a big sphere of application. But they sometimes happen to be seen as programming contests. So the first problem that we would consider, it is in some sense connected to FFT, but it's not directly about that. It's called the Karatsuba algorithm. Karatsuba algorithm is one of the first subquadratic algorithms for multiplying integers. So suppose we have 2 big integers. It's not directly divide and conquer in a sense that we do, but actually, let's see. Okay, so let's see. We have to multiply two integers a and b. What can we do? We have quadratic algorithm like I don't know. In Russia, it's told in like elementary school, or maybe in the first year of middle school. I don't remember. When you multiply digit by digit and like that sum up with a sum sheet. I don't know how it is done in Latin America, but I don't think there are many options actually to manually multiply to it. So, but what we're gonna do, we're gonna apply divide and conquer approach. What can we divide here? We can divide our integers. Let's divide them, each of them into two parts. So what I have now, we have a equal to a1 times. Okay, in our normal elementary school, we have like base of 10. Of course, when you're working on your computer doesn't like 10, you're likes 2. So probably there is the power of 2, but it's not important. Let's take some base to the power of length of the smaller parts. So the total length was n, so here is n divided by 2 approximately. Yeah? Plus a2, plus a0. So that is a, and b is the same but with b. 1 times b large plus b0. So what is a times b? It is like a1 times b1 times b to the power of n divided by 2. Oh no, already not divided by 10. Plus, like a0 b1 plus a1 b0 times b to the power of n divided by 2. And plus a0 b. If you look at this and try to apply our approach directly, what do I have? We have t of n equal to, we have 4 times. These small parts are half the size of the original parts. So t of n divided by 2 plus, and then we have to sum this all up. And unlike multiplication, adding with a linear term, the same element corresponds from the smaller weight digits to the higher weight digits, and that's all we can. Okay, let's see. Our master theorem, what does it say? A, which is 4, divided by b, which is 2, to the power of c, which is 1, is 2 greater than 1. So we're in this case. Let's try to apply this. A divided by b to the power of c is 2. So it's 2 to the power of logarithm b is what is 2. 2 of n times n squared. On the bed actually we've got the same complexity that we had without dividing and conquer. So it looks like it didn't work, but at least we see that this case is not so very bad as we thought initially. It's not exponential at least, but we don't have any problem. So to get the problem here, we need to review a little bit the formula. Let's see. We have this one. No way. Nothing to do. We need to calculate this. This one we need to calculate, but this one is the sum. So we don't need separately this and separately this. We only need the sum. And the idea is that if we take a0 plus a1, if you ignore this space to the power of 2, times b0 plus b1, you get a0 b0 plus a0 b1 plus A1 B0 plus A1 B1, and you see, if you calculate this, and calculate this, then after subtracting this and this, which you know because you calculate them, from this product, you will get, right, this sum. You do not get those two halves of this sum separately, but you get this sum. And that changes A in our formula. So it's from 4, it now becomes 3, because you only have 3 multiplications, smaller integers that you have to do. And that leads us to T of f equal to 3 T of n divided by 2. Okay, this one is a little bit bigger by 1. So, this number is one more digit, but that's not important. That's a constant. It is a plus O of 0 of f. And if we now apply our master theorem again, I would like to use that word actually. Let's write it here. So A divided by B to the power C less than 10. Let's simplify this actually. So this is what? This is A divided by C, logarithm. So this is actually let me simplify that in general. I don't.
A in power of B.
A in the power of S squared with good sequel.
Because then you can cancel.
Where did C go?
B
Let's see. It's
log B of A
in the decrease in DSU. Unite, these gets do not change anything, this return do not change anything, so unite only does change in the rank and change in the parent. What do we do? For it's usually done separately for rank and parent. We create a stack of modifications. So when we change some value, we push before changing that, we push the old value to the stack, like this. So we say, before making RFU++, we R stack push U R of U, and then R of U++. Similarly here, we make like P stack push, what was that? U P of U, and then P of U equal to U. And same here. Now, to undo the unite operation, we just pop the top element of R stack and replace the old value of R, and pop the P from P stack and replace the old value of P. And this undoes the unite operation, reverses our degenerate union to the condition before that union. Now we see why path compression was not that good, because in case of using path compression as well, we should have reversed all those operations as well. And since we would have reversed them anyway, there is no reason for us to do them, because we only increase our complexity with them, not decrease as before. Because so now with our disjoint set union with undo, we still have unite in a constant time if ignoring union, ignoring gets that we do, but new less effective get is at which complexity? Logarithm, yes, because of the rank heuristic, which is still here. So the get is now logarithm, and unite is a constant time. If we do not count these gets, we can move them outside, so do not count them here. So, and now we can undo unite. And since now we can undo unite, and since we have the regular parenthesis sequence here, correct parenthesis, this is like another stack. So when we add the DH, one moment please.
Unite equals okay.
One moment, okay, I will finish and then you'll. So when we make this, we unite, and since here it's a correct parenthesis sequence, it cancels out itself, and then if we do this, we see this, we undo unite. Another question? Yeah.
Unite equals okay, so it will also be logarithm.
Sorry, I don't have. Could you please repeat it now?
Unite, the unite function uses the get function.
I still don't hear. I'm sorry.
I think he's saying that unite uses get.
Unite uses get, yes, but we don't count them here. Just you can use gets. You usually do not count them inside unite, and you just like call these gets outside of unite. For our convenience, we put it here. You can write unite for logarithm n as well if you wish. It's not a problem. If there just usually when we want that inverse Ackermann function, it is easier to count gets outside of the unite, but it is not important actually here. So okay, but in our original problem, there is no option that there is no constraint that this is a regular parenthesis sequence. So how can we deal with that? Here is where divide and conquer comes. So they have the sequence of events, and so we would like to divide and conquer. We will divide it, process the events here, and then process the events here. How can we do that? Okay, let's see. We will consider the general case that we are going to process events on some sub-array of our original array of events. So, first of all, let's deal, we will have the DSU with undo. That will help us to deal with that. Our invariant will be the following. The DSU with undo, when we are going to solve for this array, so the subarray contains information about all edges that exist during all events of this subarray that are not created here and are not removed here. So they were created somewhere there, and they are going to be removed somewhere there. So they exist during all the length of this part of the array of events. So this DSU with undo in its current state comes when we are going to comes to us when we are going to process. For example, for the whole array, this is just an empty DSU because there are no edges that are created before or erased after. Okay, so if our array of events has length 1, then if it's not a query, then we do not do anything, because we should not answer the add or remove query. So they do not have any output. If it is the query of reach, then great. Our DSU with undo contains just the information about all the edges that exists now. So we use it to answer our query in which time we use gets, which is logarithm time. So in logarithm n time, we answer the query. Now let's. So here, now we go to the general case for divide and conquer. So if it is longer than 1, then we need to divide and then maybe conquer them. So divide it into 2 parts. And now we would like to recursively solve the problem through the 2 halves, but we need to adjust our DSU for those 2 parts. So let's see. If we are going to make the recursive call for the left part, which edges should be added to that DSU? That are exactly edges that are created somewhere before our current chunk of the array and removed exactly in the right half of our chunk of the array, because those that are removed later are already there by the invariant, and those that are removed here should not be there again by the invariant. So what we do, we go along the second half of our chunk and see if this is the remove event. We look where is the corresponding add event. If it's before the beginning of the chunk, then this is what we need to do, the unite in our DSU with undo D. So like we go, like the pseudocode will be like, so solve from L to R. So it's L, R, it's M. For I from M to R, not inclusive, if event I is remove and its pair pair is less than L, then unite. This event it U and event IV. After this, we have adjusted our D to process to be consistent with the invariant for the left part of our chunk. So we make a recursive call. Let's solve LM. Now when this recursion terminates, we need to fix it back as it was before, and this is where undo comes. We go in the opposite direction along the second part of our chunk and undo the unite operations that we did. The question?
Isn't it easier to just do seg tree?
Do what?
Seg tree, segment tree. Like when you're adding an event, you're like it's like range update, and then you do DFS on the seg tree to find the
Well, that is in some sense exactly the DFS on the seg tree, but just what are you going to store in the nodes of your seg tree? You're not going to store anything. You just but in some sense, this is like, well, any divide and conquer algorithm in this sense. Merge sort can also be viewed as a DFS on a segment tree. Just when we're talking about the segment tree, we're storing something in the nodes. What are we storing here? We do not store anything, yes? So we undo that in the opposite direction. And then for the right part, it's just symmetric. We go along the left part, look for the add events such that remove event is after R, and add them, make a recursive call to the right part, and then undo. So what is about our time complexity of this solution? Its time complexity is space. T of n is, so again, T of twice T of n divided by 2, and now about the conquer, well, divide phase maybe. It is divide and conquer here are similar divide is this and conquer is this. This unite is actually, well, for this usage, maybe it's more convenient to calculate this gets inside of unite, so rather it's also logarithm n because of this 2 gets we write as usual. So we write, so we have plus n logarithm n, yeah, for this unites and undoes. This is not exactly as it is written in the master theorem because it doesn't have like option for the logarithm there, but it doesn't change a lot here, so we have like similar. It can be played. This logarithm doesn't matter a lot, so we have just like T of n. Here is n logarithm squared. So that's it. That's the dynamic connectivity problem offline. Well, why do we put the word offline here? The answer is because we know all the queries before. We need them. We cannot do this online because, for example, when we are processing the queries in the left part of our chunk, we need to know when are they going to terminate. So we can process them one by one. Well, there is an algorithm to do this one by one, but it is way more complicated. It uses linking and cutting trees. I've heard about those. And well, I used to have a team at my university that I was coaching that had linking and cutting trees in their like team notebook, and fortunately they didn't try to use it at real contests, but at the training camps they tried to use it, but as far as I remember, never succeeded. So, but for this CP problem offline, DC problem offline is actually quite a simple code. DSU with undo is nothing really special. And this divide and conquer approach, usually the question.
How do you solve for the right segment?
Exactly the same. So you go for what you want to fix now this GSU with undo for to be consistent with the invariant for the right segment. So you need to add those edges that are alive during the whole right segment but not still there. So you go for the left part, look for the add operation, so that remove operation is to the right of the right segment, and add them to D. And after the recursive call, you undo all these operations. Your question, please?
Log from the formulas,
This
n log n.
This
This n is the same as the input from t, or like the first n? Because I mean, when you're at the given.
You mean well, okay. You see that this yes, it's different actually. You are correct. So this can be seen as a constant considering this. So this is t of n is twice t of n times logarithm original n, and that is even better for us because it's now kind of the constant for this formula, so we can apply the master theorem. And this is logarithm n, and this logarithm n d becomes logarithm of our normal n again in the final form. It's even better for us. Yes.
Just for curiosity, what would be the complexity with linked tree?
I think it would be the same, maybe even with one logarithm, not squared. I'm not absolutely sure, but I don't feel that it's worth it. Because besides the time complexity of the algorithm, there is the time complexity of its implementation, which is different. Okay, before going to the coffee break, the last algorithm for today, unlike no, for today, of course, for the first part of today, the Fourier is awaiting us again. Now, the last algorithm for the part until the coffee break, unlike the previous algorithms, which I recommend using actually, because well, I don't know about Karasuba, maybe if you master Fourier, it's not very important, but it's easy and it's a good demonstration of this technique. But the DCP offline and the Z function, when you meet this problem, you know what to do with that. But this algorithm was used like for 15 years, but then the easier algorithm was invented for this problem, which I will tell you on Saturday, on our geometry day. But now I will, for the sake of completeness and for you to see the idea of using divide and conquer in geometric algorithms, I will show it to you. Maybe it can still be used in some variations of the problem when the other technique could not be used. That's two closest points algorithm. The question is, you have points on the plane, and the question is find two closest points. So two such points that the distance between them is minimal possible. The naive algorithm works in quadratic time. You just iterate over all pairs of points. We will consider now again the good algorithm, but there is a simpler one. So take it into account, but for the real contest, I would recommend using, for this very problem, I would recommend using the simpler. Okay, nevertheless, let's consider it. So let's sort the points on the x coordinate. and use divide and conquer. So let's divide them into two halves by taking the median point and this is the left part and the right part. So there are, again, similar to the tandem repetition question, there are two options. Either there are three options, but two of them are similar. Either two closest points are on the left of the division line, or 2 points are on the right of the division line, or they're on the different sides of the division line, which is the tricky case. So now what do we do? These two options are easy to find. We just to consider. We just recursively solve the problems for two halves and choose the minimum value. So let this minimum value be d. Sorry, minimum value of arms left and arms right. And now we would like to find the possible solution on the so that the points at the different sides of the line. Let's see. First of all, the only candidate points that we would like to consider are not further away from this line than D, because in this case they would definitely be more than D apart. So we like measure D here, and consider two stripes of with D, and only consider points there. Let's take points there and now sort them by y-axis. We would actually not sort them every time. I will tell about this moment in a moment. But now, temporarily, let's think that we just go through all the points, take those of them that are in this area, and sort them by y-coordinate. Now we're going along the y-coordinate, and what do we do? Let's see. This is the point that we are interested in, and we want to find some point that is closer than D to that, and that is also on the other side of the separation line, because if it's on the same side, it's already considered. It is not further away than D along the y-axis, clearly. And so we have like this D times 2D rectangle here. And it consists of the square here and the square here. And we know that on one side of the line there are no 2 points that are closer than D to each other, because D is the minimum of the two answers for the halves of the points. So how many points can be there in this rectangle? Well, the simple upper bound is that there are at most 4 points here. You definitely cannot fit more than 4 points in a square, in a unit square at the distance at most D. Yeah? And similarly, at most 4 points here, including R1. So if we, this trick you sometimes may be used to cheat the judges' test cases, like you make some dynamic programming or some event processing algorithm, but you only consider a few events in the past, or only consider the chunk of length up to maybe 100, is to reduce from the quadratic algorithm to incorrect linear in a hope that it would pass the judges' tests. Yeah. So this is a rare case when this can be proved that this is what you should actually do. So you iterate through these points, but for any point you only consider the previous 7. No necessity to consider more, because they would not fit. They would definitely be more than D apart from this one. So if we didn't sort, that would be a linear with a constant of 7, but sorting seems to make it an logarithm n, but actually you do not need to sort. What you need to do is you need to have, well, this is actually the recursive algorithm, as all divide and conquer algorithms are. So you have like piece of point, chunk of your points by x coordinate. So you also pass to your recursion their order, so a separate array of the order of these points if they were sorted by the y coordinate. And since you anyway you are passing through all these points, you can pass, and if you can also pass, for example, when you're going to make a query from left to m to middle, you go through points, and if it is sorted by y coordinates, and if it is in the left part, you push back it to the array of sorted by y coordinate for the left recursion part, and if it's not, then for the right. Make this two columns. So now you have these points already sorted by y coordinate. Do not forget that for this heuristic to be correct, that you only consider the last 7, you again, before going through them, when making a contour part, you need to only keep the points that are at most at the distance d from the separating line, and after that you can process them in linear time, and that gives us our favorite formula of t of n twice t of n divided by 2 plus O of n, which is n logarithm n t. Okay, at this point I think we will make a coffee break until let's make it 10:15, and please come back at 10:15 for the second part of the lecture.
Esa por acá. La que por acá se quedó.
Everybody has returned? Okay, let's move on. Our lecture today. So now what we're gonna discuss is maybe one of the most famous algorithms based on divide and conquer, which is fast Fourier transform. It would be easier for me to tell it to you than to high school students or middle school students because I believe you know the complex numbers. Home. So, okay, so actually, the topic that we're going to cover, discrete Fourier transform and its fast like that, was not ever invented to multiply numbers or whatever we're going to do with that. It was developed initially as an internalization, as a translation maybe of the continuous Fourier transform to discrete data for discrete signal analysis or finding some frequencies in the signals and so on. But when the competitive programming became popular, the people eventually found out that it can be used for some interesting, that it has some interesting applications in competitive programming. And that is what we're going to go through today. If you're having your majors in like electrical engineering or maybe some branches of computer sciences, you might have heard about it, or maybe you will hear about that in the context of signal processing. But we will not go into that. So what is fast Fourier transform, discrete Fourier transform? Let's consider an array called A of length n. We will index it from 0 to n minus 1 essentially. We will, for the sake of this algorithm, it would be more convenient to consider n to be the power of 2. So we will say that n is 2 to the power of m. For most applications that we will consider, if it's not the power of 2 in your input data, you can expand it with some neutral elements like zeros or so to get into the power of 2. So these are elements for, again, for the sake of, we will have two parts actually for this. The first part we will consider the elements of the array to be these numbers. I remind you that complex number has the real part and the imaginary part, which is denoted by I, usually in mathematics, and by J for some reason in C++. I don't know why. Maybe I know why. So probably it is from the part where to distinguish it from 1, when 1 and I were very similar. I think it is from those. So, and it also has the exponential form of some radius times exponent of I phi, in which phi is the face of the number, it's kind of an angle, and r is the modulo of the number. So if you put it on the Cartesian plane, then it's like this. It's A, it's B, so it's the real imaginary part, and r is the radius, of course, the distance from the central point, and phi is the angle usually measured counterclockwise from the x-axis. So this is then r times cosine p plus I sine. So if you're in this form, it is easy to raise complex numbers to some powers. So if you consider r to e to the power of ip to the power of k, then it's clearly r over k times e to the power of I times k times v. So you see that the radius is raised to the power of k as well, and the phase is simply multiplied by k, which is the property of the epsilon. And we will consider numbers on the unit circle, so that r is 1. And in this case, this doesn't matter because 1 in any power is 0. Well, it's 1. 1 into any power is 1, and so you only multiply the phase. So when multiply, so if you say it's 1, so it is the unit circle. So when you multiply, when you raise these numbers to some power, it just like rides around the circle, goes around the circle, and raise it to the power of k, multiplies its angular value by space by k. So we will be interested in so-called primitive roots of unity. The primitive root of unity is such of the nth power is such value omega n, that omega n to the power of n is 1, and it's not 1 for any smaller power, integer power. So for any 1 less or equal to k less than n, omega n to the power of k is not equal to 1. There are potentially many roots of unity. Actually, I think there are approximately number of co prime to n numbers around the circle, but we will use the most easy to notice one, which is e to the power of I twice pi divided by n. It is clear that if we raise it to the nth power, it will be e to the power of I times twice pi, which means that we should make it a full circle of 2 pi of twice pi and get area, which is 1. And for any smaller power, we're not going to get there, so it's not. That is why, so we will, n here is the same, n is here as here. So that's why we need complex numbers here. For real numbers, we don't have primitive roots of unity other than of power 1, which is 1, power 2, which is minus 1. For power 4, for example, it's already I, yes, which is not a real. In real numbers, okay, so what is a discrete Fourier transform DFT and A? Let's consider our array A as the coefficients of a polynomial with and the variable we will use the name t, so it's a0, t, is a2 t squared, so it's a n minus 1 t to the power of n minus 1. And we will put powers of the primitive root of unity of nth power to this polynomial as values for t, and look at that at the results. So we have omega n, and we will have some values like p0 will be this polynomial, is A of T, so it depends on the T, is A of omega n to the power of 0. Omega n to the power of 0 is 1. So if you look, it is just the sum of elements of the array. So when you put T equal to 1, you get just the sum of all the elements. Yeah? So B1 will be A of omega n. And so on. So B with the index of I will be A applied to omega n to the power of I. Like this. And so on. So this will get us the new array B. And that array is called the unnormalized, actually, discrete Fourier transform of A. Why is it interesting for our problem? The thing is that, let's consider this polynomial A of T. So what do? To store the polynomial, one way to store the polynomial is to store its coefficients, like we do here. Just say A0, A1, and so on, and n-1. But there is an alternative. Instead of, storing these coefficients, we can store the values of this polynomial at some points. How many points do we need? Actually, for the polynomial of the power k, we need k plus 1 point. For example, for the linear polynomial, we need 2 points. There is one line for any 2 points. For the polynomial of the second power, like the quadratic polynomial, 3 points. There is a unique parabola going to 3 points. Line, but and so on. So in our case, we have the polynomial of n to the power n minus 1, degree n minus 1, and so we need n points and distinct points. If we know the values of our polynomial and n distinct points, we can actually recover our polynomial. There is a general solution for any points, which is called Lagrange polynomial for that. Lagrange interpolation polynomial. It's usually taught in the calculus classes, but it turns out that if we choose some particular points for that polynomial, not arbitrary and distinct points, this very and distinct point, the powers of the primitive unit, root of unity, then both operations of finding that representation and going back to the normal coefficients representation can be made faster, actually in n logarithm n time. That is not exactly true, to be absolutely honest, because when you are doing all this stuff, you're actually working with the floating point numbers, and you cannot make absolutely precise time floating point numbers. You can make them absolutely precise at all, and if you carefully analyze for any application that requires precision, you see that it grows with the growth of n as well, and therefore you would need also a factor here that takes care of that growing precision required for storing that number. But for the sake of most competitive programming application, it doesn't matter. Their usually coefficients are usually integers, and I will give you the trick that after some processing some data that involves Fourier transform, that you know that in the end you get integers, you just get not integers because of the floating point precision losses, but you just round that. Usually that's usually sometimes no, but as far as reasonable sizes of data are involved, like 100,000, 200,000, 500,000, so embody the benefit of such representation of a polynomial. Suppose that let's start with the most primitive application of DFT, which is number multiplication. I already know the Karat's algorithm for number multiplication, and what we are now is FFT for number multiplication. If you look at this, you see that it is quite similar to how the positional systems for writing numbers work. So you just have, instead of t, you put the base of your number, of your scalar system, like 10 for ordinary counting, and maybe like 2 to the power of 32 for long integer representation in your computer. And multiplying these polynomials exactly corresponds to multiplying these numbers. Clear? It does not be clear. But if you represent the polynomial as its representation at points, let's see what happens when you, for example, add the two polynomials represented by its values at some points. They just point-wise add up. The value of the sum of two polynomials, a plus b, at the point t is actually a of t plus b of t, clearly. But the most funny fact actually is that for multiplying is the same. So when you multiply two polynomials, a times b of t, you will get the point a of t times b of t. Exactly the product of the values for the original. And that means that if you represent your polynomials like this, you can multiply them in linear time. You just point-wise multiply these values, and you get the values for the product. There is a small problem that the new polynomial has the higher degree, twice as high, and so you need twice as many points, but you should care about that beforehand. So when you know you're going to multiply polynomials, of course you save their values not at their current degree number of points, but at the future desired degree number of points, like twice n, for example, if you multiply polynomials in degree n. Twice n, fortunately, is also the power of 2. Okay, so this representation is very nice, and we can add, subtract, and multiply polynomials in this representation in linear time as far as there are enough points. If you overflow the number of points, if the degree of the polynomial is too big, then you go to the inverse of kind of taking it modulo some polynomial, maybe. Well, the results are meaningless if you exceed. So you exceed the degree, so you must take care of calculating that beforehand. But after that, you can move all your polynomials that are corresponding to your number that you can work with to this form using DFT, which has an algorithm that we will now consider. It's called FFT. So fast variations. Then work with the polynomials in this form, and then go back. If you need to print them as numbers, for example, you can go back to the original form to see what's going on there by using inverse DFT, which will turn out to be almost the same as the forward, the original FFT. So, do you understand the idea? So the only missing thing now is the fast algorithm for calculating DFT, and this is where this, again, everything that I have said so far can be applied to any n distant points. But our idea for this point would be to calculate the DFT fast, because if we take arbitrary points, then it would take quadratic time to make this transformation, to calculate this way, because we need linear time to calculate this, linear time to like this, and they are not connected to each other in general things. But in our case, when it's powers of the power of the root of unity, we will see that it will help. Let's go. So what do I want to know? What do I want to do? We want to calculate A from this value. Okay, let's write it out. It's A0 plus A1 A n to the power of I. It's A2 omega n to the power of 2I plus 1 plus A j times omega n to I multiplied by j plus and so on plus n minus 1. So usually in divide and conquer algorithms, we split our data into two parts, the first and divided by the last. Yeah. But in this algorithm we will do a little bit contrary. We will split by odd indices and even. So that would be A0 plus A2 omega n 2I plus A4 omega and 4I plus and so on. Plus, and for odd indices, we say that they all have omega n to the power of I, 3I, 5I, and so on. So we can take omega n to the power of I out of this parenthesis, so it's omega n to the power of I times A1 plus A3 5 4I plus and so on. Now, if we remember what is omega n, omega n is, we make that rotation of 2π divided by n. What is omega n squared? Remember that for complex numbers it works like doubling the angle. So it is now like twice 2π divided by n, which is, it's tempting to say 4π divided by n, but we will do another thing. We will say it's 2π divided by n divided by 2. Fortunately, n is can be divided by 2 because of the power of 2. And that is exactly omega n divided by 2 because it's the same formula for that, yeah? So, if we look at this again, we see that if we take this 2 inside, then that would be, alright, right here, A0 plus A2 omega n divided by 2 to the power of I plus A4 omega n divided by 2 to the power of 2I plus and so on. And here the same, A1 plus A3 times omega n divided by 2 to the power of I plus A5 times omega n divided by 2 to the power of 2I plus and so on. So this is exactly the same thing that we're doing with our original array, but for the arrays of the size twice shorter. And the correct value of omega n, which is omega n divided by 2 now. And that means that this is exactly the same problem, which can be used using the same algorithm, the recursive algorithm. So what do? We divide our array to even numbers, and even indices and odd indices, make the same transformation recursively with those parts, and combine them using this formula. So it is, it can be rewritten as a, let's call this array of even indices, say A0, so it's like A0 omega n column and divided by 2c to the power of I plus omega n to the power of I times a1 of omega n divided by 2 to the power of I. There is a small, actually there is a small problem when I is greater than n divided by 2. What is the problem? There are, if we make recursively these two Fourier transformations, they have the length of n divided by 2, so they don't have such big indices. So there are no indices greater than n divided by 2. Fortunately, omega n divided by 2 to the power of n divided by 2 is 1 by definition. So if I is greater than n divided by 2, then omega n to the power divided by 2 to the power of I is omega n divided by 2 to the power of I minus n divided by 2. So here we just reuse it again for the higher numbers. This one changes. Actually, you can clearly see that omega n to the power of n divided by 2 is minus 1. It's omega 2, which is minus 1. So, but this argument is not changing at n divided by 2. So let's draw the picture. So we have like our array A, which is even indices, and then to an array ABO. Then we take odd indices and take them to array A1. Then we recursively create the transform the array called B0 and B1. And then we do what is called, because of how it looks at the picture, the butterfly transformation of these two arrays, which is actually for our divide and conquer algorithm is the conquer part. Well, yes. Sorry, guys on the stream or the guys on the future that are watching this lecture, but you didn't get anything because we were. I don't know. Maybe you caught anything. Just prepare and make it very, very loud. And back here, I'm sorry. So it's called the butterfly transformation. We get the array B from this. Very good. So we take, let's look at this formula. For this element, we take this element from here. We take this element from here and multiply it by, well omega n to the power of 0 in the numerator. Let's call this multiplier. I don't know, x. Multiplied by x. Now for the second half, as I have told you, this is index 0, this is index n divided by 2. We take this one again, and we take this one, but we multiply it by minus. And that reminded probably the authors of this algorithm, which are actually Cooley and Chucky. There were two guys. When it was Fourier transform, it was not Fourier. Fourier was long dead before the computers were invented. So there were Cooley and Chucky who went to this transformation, and they looked at this picture and it reminded them of a butterfly, which probably does. And they called it the butterfly transform. So, okay, this is actually that. that's all. If you see, that's not all actually, but this is the hardest part is already behind. So we have like our favorite T of n is T twice T of n divided by 2 plus O of n, which resolves using Master theorem, which is from the n logarithm. Okay, so getting back to this, let's look at this picture closer. You see that unlike most of our previous algorithms, both divide and conquer are non-trivial because in most algorithms either divide was trivial, just recurse, or conquer was trivial, just you have sorted 2 parts, great, so very likely to do so. But here, divide seems to be not trivial, I have to put even guys here or guys here. And conquer also seems not trivial, like make this butterfly. But the truth is that the divide, let's look closer at what's going on the central recursion with this divide part. So let's see. Let's take an example of an array of length 8. 0, 1, 2, 3, 4, 5, 6, 7. At the first step, we put the even elements for it here. 0, 2, 4, 6. And even index element, or then even odd index elements then. This picture shows it as 2 different arrays, but in the implementation, of course, it would be more convenient not to create multiple small arrays, but to use the original, or maybe not original, helpful auxiliary array, but one array for both paths. And as usually in the recursion, pass L and R, like in merge sort, like in the ICPC, and like in most other algorithms we have discussed. So for this purpose, we will just rearrange the numbers in a way so that even indices go first, odd indices go next. That would be 1, 3, 5, 7. Okay, let's go deeper into the recursion so that first part, when it goes down, it has new indices, which are these divided by 2. So it's 0, 1, 2, 3. And again, the even ones go to the first part, 0, 4, and the odd parts go there, 2, 6. And now again, here are the same, like 1, 5, 3, 7. It looks, well, the next thing, just they would not rearrange because for the next 2, 0 is even in its first and 1 is in its second. So we see that this is just the permutation of the original elements of the array, but what is the nature of this permutation? How is it organized? The answer is, so you see that the first part is those that are in their binary are even, so their binary representation, that's 0. And those are the numbers that have binary representation and terminating with 1, ending with 1. From among those, these are those who are after dividing by 2, so the second last binary digit is 0. The second last binary digit is 1. The second last binary digit is 0. Second last binary digit is 1. And if we write the binary representation, we see that actually what we have is that we have this binary indices, but in the reverse order. So we put the element to the position which corresponds to its reverse order. So if you read it from back, it's 0, 1, 2, 3, and so on. So you just not reverse the array, but reverse the index of the array and put the element to that position. That would make all your divide steps in one step. And here again 0, 1, which is 4 one way from backwards. So that is called, again, by the authors of the algorithm, the magic permutation. Not so very magic, but really funny. So after you do this magic permutation, all that is left is a contour stage. And if you look carefully at the contour stages, you see that they're essentially the same. Because what do? You at the first step you apply this very small butterfly of size 1. At the second contour stage, you have a little bit larger butterflies of size 2 that go like this. So this one goes here, and actually the same one shifted by 1 goes here. Yeah? And here is the same. Like this. And then the final contour stage, the bigger butterflies of size 4 this time, but of course for this arrays of size 8 you wouldn't do all this stuff. Generally from like 15, 16, 17 such stages. And what you can see now that although by the nature of the construction it was the divide and conquer algorithm, finally we see that the recursion is not needed because all the divides can be implemented in one application of magic permutation, and all the contours can be implemented again by logarithm n minus 1 probably. No, not minus 1, but logarithm n butterfly passes. So you just need to divide it by these chunks and maybe the shooting dark lines too. So this is actually the like 10 lines of course, and nothing too scary. I don't know, for some reason, at least some time ago, people consider the FFT algorithm hard, one of the complex topics, but I think that implementation-wise it's easy. It may be hard to note that you need to use that. It may be the case. But for the implementation, it's quite easy. If you can do it one, for example, go to common sources, Google for FFT tag, write this code, and just make sure that you know it, put it into your notebook, and it will not be. It's not like link capturing. It's short and diagram. As far as I remember, in the last year there were 1 or 2 problems that were found that involved 15 there, so it can be useful actually. They do give such moments nowadays. Now, talking about FFT, let's cover one more thing, and then look at some applications. The question?
Didn't quite get what you do on the butterfly step.
Here, do you understand this picture?
Yeah, I didn't understand what you're doing.
Didn't. Do you understand this formula? And we are applying absolutely this. So A0 of omega n divided by 2 to the index of I is exactly the B0 of I. This is exactly in the notation, yeah? That is exactly B1 of I. So this is B0, this is B1. This one I denoted as X. And so we add B0 and B1 multiplied by X here. And since this array is only half of the size, for the second half here, it just cycles out. So you go again to this element, actually, because all this and this correspond. So we go on here, and this one is also going here, and this one is also going here. But x now for those elements is for the real value of I. This is not inside this recursion, so it's the real value of I, which is n divided by 2 greater, and omega n to the power of n divided by 2 is minus 1. You can clearly see it, like rotation here of is minus 1. So that's why you can do all these two assignments in one step, not to deal with modular here, this plus this, like u plus v and u minus v. U is v0i, and the v is v1i times x. Okay, any more questions? No more questions. Okay, so the next thing that we're going to discuss related to this is that sometimes it's not. Well, I promised to tell you about the component. So, when you are solving the problem, consider the problem of multiplying two integers. We look at the integers as polynomials like this. We make f of t, we get this. We pointwise multiply this, and we want to get back. How to get back? There are two ways to get back actually. The first way to get back is to apply what is called the inverse Fourier transform. Well, actually there is one way to get back to apply inverse Fourier transform. There is just two ways to do this. One is to use omega n inverse as the basis. So you just do the same, but instead of omega n, you use omega n inverse, which is e to the power of minus 2 pi divided by n pi. I used to do, after that, you will, if you put this into formulas, I will do this now, but for the other one, you will get your original array multiplied by n. So if you the discrete Fourier transformation is actually a linear transformation. You can see it's actually multiplication by the matrix. So what you do, you can see. I think that this is this clear for everybody. No more questions on this formula. Can I read it? So if you look carefully, you can see that actually f of t, d of t of a seen as a vector can be seen as matrix multiplications. Like 0, a1, a minus 1, and here is omega 0 to the power of 0 over n, or 1 again to the power of no 0, 0, 0, 0, omega n to the power of 1 and to the power of 2. Oh my god, no, 0, 1, 2, so on, n minus 1, and for 0 again, n to the power of 2, 4, and so on. So actually, putting the value into the polynomial is like scalar multiplication of this polynomial coefficients with the row of the powers of the corresponding value. Yeah? So this is, by the way, called van der Waals matrix, which is the matrix of powers or something else. So what we would probably like to do is to find the inverse of this matrix, which is almost the same matrix, but here minus. Okay. If you do this, look at this. Omega n to the power of minus 0, well, minus 0 is not so important. Omega n to the power of minus 0, omega n to the power of minus 1, then to the power of minus. n minus 1. If you look at this, then when you multiply these matrices, you will see that they will actually like cancel out because this matrix is symmetric actually. It has omega n over ij at the position ij. So it's symmetric. And if you multiply, you will get they will represent the sum of n ones, which is n. So you will see that and for different rows, it can be said that it goes to 0. So the product of these two matrices is the matrix with n's at the diagonal, and what we want to do once at the diagonal. So this is so-called expanding linear transformation. It expands all vectors into actually now since planet twice gives us multiplication by n by a root of n times. So what you do, you apply the same thing but with this and divide by n. The funny thing is that if you instead put the same transformation again, so suppose you do dft of dft of a, what would you get? Surprisingly, you will get a very strange thing. So, I remember correctly, a0 will stay it will be n again multiplied by. A0 will stay at its position, but all other elements will go in the reverse order. So it will be an minus 1, an minus 2, so a1. So that is like reverse and shift by 1. For some reason, you can just put it into these formulas and see that this will be like. So this matrix, if it's squared, not multiplied by this, but square, we'll get like kind of matrix of n's, but n, this one, not the one like unit matrix, not divided by the but with others. So for me, this way is easier to handle because you don't need to take care that you have different bases, different roots of unity inside your FFT. You have just one plot for FFT. If you need the inverse, you apply again, reverse there. But don't forget, do not touch the zeros position. For some reason, it stays where it stays. And again, don't forget to divide by n. So if you see from all these various operations with complex numbers, which are represented, of course, usually as a pair of real numbers, you have a lot of precision loaders, and especially this division by n, low chance that you don't get any precision loaders, and that they will be integers, in fact. So the third thing here is that you should not use that very big T as that very big base, this maybe 2 to 32, maybe because floating points actually don't have a 64 significant digits, they actually have as high as another 51 significant digits, or 48, something like that. There are 50, okay. And that's why you should probably use like 20 significant digits to the row 20 originally for you, because you will also have like this would sum up with that classical multiplication. You not only multiply one by one, but also sum them with a shift. So it's also multiplied by n. So the numbers here after multiplication will be proportional to like n times your base squared, and also remember this n it's like n squared. So base between 2 to 16, 2 to 20. It is recommended not 2 to 32. But, and also, of course, overflows since Fourier multiplication is multiplication of polynomials, not digits. The overflow between digits will not be applied by the Fourier itself. You need to normalize your digits back by going through this and moving the overflow forward. As well as you do when you do like this, and so carry the overflow forward. So that, but however, it can be used like this for multiplying digits, multiplying numbers. However, in some situations, you would prefer not to work with floating point numbers. I will give you one argument for still using floating point numbers. The architecture of modern computers is such that there are two separate processing units working with integer numbers, including like memory, addresses, and so on. So the indices of array and the floating point numbers. And that means that it actually speeds up your code if you use parallel. When you make some floating point calculations, and after that, before using that result, you make some integer calculation, like maybe finding the index of the next element in the array, going to the next iteration. So the smart system inside the processor of your computer it's not fully synchronized. It doesn't wait for the result of the floating point calculation. It continues working with integers, and only when the number is needed, actually, it starts and waits. So floating point implementation is usually working better than the modular implementation that we will consider now next. However, there is floating points have other disadvantages, like being imprecise and taking care of a number of significant digits, especially if you have a lot of calculations. This can be done. So what we need actually, let's see, why did we use floating point numbers again? Because we needed the primitive root of unit. Can we find another algebraic structure different from complex numbers that has multiplication, addition, and primitive roots of unit? The answer is yes, and that is we need fields of prime signs, but for some special prime numbers. Let's look at that. Actually, from algebra, you may know that, well, first of all, the field. The field is the algebraic structure that has multiplication, division, addition, and subtraction. So, we actually, at first sight, we don't use division, but if there should be division, there should be a field for the whole that's for the word. So there are well-known fields of rational, real, and complex numbers, and there are also finite fields. They exist, and there is a unique finite field actually for the powers of primes. But for the purpose of our discussion now, we will only need for the first power of primes, which are just integers modulo that prime, with multiplication modulo that prime, division modulo that prime. All these numbers modulo this prime will be inversible, except 0, which is normal for the field. So the important thing about these fields modular prime is that their multiplicative group is cyclic. That means that all the values are actually the powers of some value. So this field consists of 0, 1, so on, and p minus 1, these numbers. And all of them except 0 can be represented as some number g to the power of 1, g 0, g to the power of 1, so on, g to the power of p minus 2. This is for every prime p, there exists such number g that all these p minus 2 numbers are distant, and they are a permutation of non-zero elements of this field. That is a fact from algebra that we of course will not try to prove now, but we will use it. This G is called the primitive root, actually, or the generator of the multiplicative group of this method. So our now, since it is cyclic, if we write down here the next element of this geometric progression, g to the power of p minus 1, what would it be equal? 1. So this is 1 and this is 1, and then it will go on a cycle. That's why it's called cycle. So, what we would like here to do is we would like p minus 1 be equal to n times some k, which is 2 to the power of m times some k, some g. So we want our p be 2 to the power of m times some t plus 1. There are so many prime numbers actually that there are many prime numbers of this form. One well-known such number is often used sometimes as a clickbait, sometimes no. In programming control statements, it starts with 993 or 998. And it has like 9 digits. I don't remember it exactly, but I am sure you have seen that. Like 998, you say. A something 3 in the end. So this 9-digit number has this form. It's like 2 to the power, I don't remember, maybe 1121 times t plus 1, something like that. Maybe 22. So how can we make use of that fact? Let's say that omega n is g, this number generator, to the power of p minus 1 divided by t. Divided by 2 to the power of n, divided by n. And if we make omega n to n, we will get t to the power of p minus 1 equal to 1. And for any smaller number, we will not get 1 because it's a cycle, so we will be somewhere, we will not reach the end of the cycle yet, so we will get something known. So this value, it behaves exactly like what we want from our primitive rule of unity. Here it was cycling around the center by the unit circle. Here it is cycling in some sense through these numbers in some order, but the result is the same. So you can apply discrete Fourier transform with that in making your calculation modulo p and using this number as a primitive root of energy of your desired power. So what? There are sometimes if you know that the answer that you're looking will not exceed some big value p, like this one, for example, you can use it for whatever problem you have, if it does probably exceed. But sometimes, if the authors of the program consider think that you should use Fourier, they will use this as a model. Of course, when we started to do this, people started to guess, oh, I see this model, this must be the solution using fast Fourier transformation. So what I will do, I will, as a problem setter, I will use this model every time, so that you cannot guess. Should you? Unfortunately or unfortunately, the fashion for this has passed like 5 or 10 years ago. So sometimes you see this, but not as often as maybe 5 years ago. Everybody always used this model. We want to hope the page here. So, what we're gonna do now? The only problem is you may have this model, or you can have this already in your program statement, or you may have this, find this using like iteration over t and check it for programmability. Since you can do it, you do it offline, you don't need to create it when running the program already at the judge's system. You do it on your own computer, so it doesn't matter, but checking programmability in root is okay. And there are again so many prime numbers, so it's not difficult to find the one. You're going with a big step of 2 to the power of 10. But the next problem is about g. You need to find g. Here, the answer to the question how to find g is that again there are so many generators actually. I don't remember the exact statement, but there is a mathematical statement saying that if the extended Riemann hypothesis is true, then there are at least logarithm n to the power of 5 divided by 2 or something like that of those generators, but it doesn't matter for us. The fact is there are very many of them. If you pick up a random g, there is a big chance that it is a generator. Not so big like 90%, but big like maybe 0.1%, which is enough. And we just need to find one. So if we iterate over 1,000, it's okay. One of them is like this. For this very number, you may remember one. I don't remember actually, 3 or 5. You can also not pick random, but go to small numbers. It doesn't matter. There are again very many of those. The only problem is how to check that it's correct, that it's really a generator, because going through p variance, where p is about 10 to the power of 9, a billion powers, a set of billion is not good, but you can fasten it, you can make it faster with the following observation. So, g to some power k is 1, always, for every g, not only generator. And this k is the divisor of p minus 1. So, since p is your number, it is usually easy to factorize because it's divided by a big power of 2 already. And anyway, you can factorize it using like square root method. It is not that big, it's like kind of billion. So, you can iterate over all divisors. Sometimes, if you want to speed it up even faster, it's enough to iterate it over divisors for the kind p minus 1 divided by the prime divisor of p minus 1. But actually, for the purpose of finding that some g, it's okay to iterate over all divisors. There are no many of them. So after doing that, you find g, you calculate this, and the code is the same. All these things are the same, just instead of complex numbers, you use modular arithmetic modular. Okay, questions? Well, I guess from what I see from my perspective, there are a few, maybe from 1/3 to 1/2 are still okay, and the other are already sleeping. Okay, to wake up, that's because there were not enough coffee on the coffee break. Okay, no problem. Now, another 10 minutes and we will go to lunch. And they have coffee in the lunch area, if you didn't notice that, in the far corner from the lines with the food. Okay, so now what I want you to do is that multiplication of integers is actually not the main reason for FFT, even in competitive programming. So I will give you several examples of problems that utilize the main idea of FFT, that is the fast way to multiply polynomials. First example, let's say we have like an array of integers a0, a1, an minus 1, and we want to find no, let's start with another representation. Okay, we have the string, two strings, S and T, consisting of two letters for the first example, A and B. Maybe four letters like genome, A, G, C, T. What we want to do, we want to circular shift one of the strings by some value. And then we match them to find the number of matching characters at the same position. So we count so-called Hammond distance, the number of positions that have the same character. Or distant character doesn't matter because the total number is fixed. So your purpose is to make such that the Hammond distance is maximum minimum possible, both are solved with the same algorithm. Let's say minimum. Hammond distance minimal possible, maximum number of matches. How can we do that? Okay, let's iterate over letters. For example, take the letter A. Let's make the array with ones where the letter A is written, and zeros where the letter B is written. So what do we want to have? We want to, if we consider it as a polynomial, we have like sum of those powers of t that correspond to letters A in the initial string. So S of t is like t equals 0 plus t to the power 1, 2 here, so 3 plus power of 3, 4, 5, 6, 7. So, same thing for the second array t large, like if we shift t by k, it is the same as multiplying t by k, but we have a circular shift. To adjust for the circular shift, let's duplicate s. We like make s twice as long. And then t may be considered not a circular shifted twice, but just shifted to the right. And that corresponds to multiplying this polynomial by t to the power of k. And we want to find the number of pairs matching here. And choose such k that it will be maximal. The trick is to reverse the string t here. In this case, that would be t in n minus the first position plus 1 plus t n minus the last position. So after you multiply, if two ones are exactly at the distance of k, that product would go in the product of s times t. The product of two ones that are exactly at the distance of k will go exactly to the position, like if I minus j is k, then n minus j is k plus n minus I. And in this product, it's multiplied by I, and it adds up to the coefficient for t to the power of k plus e. So if you multiply s by t, the coefficients starting from the one at the position n are exactly the number of ones that will be matching if you shift by the distance of k. For 0 it will be t to the power of n, for 1 to the power of 1, and so on. Questions?
I didn't understand how do you reverse t, like you replace t to the I
Yeah,
by
again, this one, I just say that t is indexed in the reverse order.
okay. So you replace like t to the I by t to the n minus 1 minus I.
Yes. Just reverse. Right. Okay, so we do this to match A's, and we do the same to match B's, and maybe if there are more characters, like again, I have seen this is a very problem with something for kinds of genome analysis, actually no real connection to genome analysis, but that was the background story, and there were 4 letters. Let me give you the final trick here. You see that these polynomials actually are of real numbers, but the Fourier transformation can work for complex numbers. And in some sense, the real and complex numbers are almost independent. They are dependent actually because I squared is minus 1, but in some sense. So, if you want to make the, if you can make your mathematical model so that you make 2 calculations in parallel with real numbers and with complex numbers, then you can make 2 Fourier transforms in 1. That is what we needed actually in this problem. Let me understand how to do that. So, if we make 1 for A and like I for B here, not 0, then matching A's would give us 1, and matching B's would give us minus 1, which is bad, they would subtract. So for the second polynomial, we will use minus I for B, and thus matching A's would give us 1, matching B's would give us minus I squared, which is also 1, and they will sum up. And matching A matching to the B will give us I or minus I, which will only influence the imaginary part of the result, which we will drop away. So we will match both A's and B's in 1 Fourier transform speeding up to 10. Not a big deal, but sometimes it's as far as I remember, and that problem was for the genome, we needed 2, not 4. Say that. So we needed this trick. Well, anyway, it's useful to know this trick. that you can really get use of imaginary parts as well. Okay, the second problem is that I want to discuss, and the last I think before going to lunch, is sometimes polynomial multiplication can be used to speed up some kind of dynamic programming. It is actually the part of a more general topic of so-called generating functions. But in a sense that we are discussing now, consider some dynamic programming on a tree, for example. So you have like this, and you have some dynamic program, and here you have an array, and here you have an array, and that corresponds to that you are distributing some number of objects between left subtree and right subtree, and you put k here, and so like kind of I minus k here, and you want to get the dynamic programming back. What you need is to make something like the number of ways. If you go k here and I minus k here, which you have from the dynamic programming for the subtrees. So you multiply them and you sum that up for all possible k. That is, well, why common situation for the counting some way to mark like k vertices on a tree with some conditions. What can you do? It's already obvious, I think, for some of you, that this summing up some a b for k from 1 to some number n a k times b I minus k is ci. You consider this is exactly polynomial multiplication, and that is exactly what I have just split up. So we just know how to multiply polynomials and logarithm n time instead of square time. So this can speed up this dynamic programming calculation from and square the vertex to like n log n in the vertex. And the additional trick that can be applied here is that you can actually do a little bit better in the following sense. If you have absolutely this polynomial transformation at your level, so if you don't need the real representation of the coefficients, and this is exactly polynomial multiplication, so there are no like other modification of this data. So that maybe there are some shifts or adding constants which can also be like represented like polynomial operations. Shift is multiplication by t, adding constant, adding some polynomial with a constant value. So if you are, then you can actually store all your dynamic programming tables as Fourier transformations of the corresponding polynomials without going there and back with that representation at each node. And that saves you logarithm n, which is, well, not very expensive logarithm, but the fewer, of course, the fewer transformations you make, the faster your program. You only make, usually for the leaves, there are some trivial solutions which can be found already in the required representations with some kind of constant or t or whatever. And then you keep this, and only in the root for the final table you make the inverse of t and get the required programming. That is another trick called. This is actually a general trick again called generating functions. When you generate a function is just this polynomial. In general case, it is for the series, not for the polynomial, but for computation it's usually a polynomial. So generate function allows you to represent the array as some in some compact form, usually, and in our case, in the form of this Fourier transform. Okay, that's it. The trees, unfortunately, were the victim of Fourier. So, no, the trees were saved, and all the rest we have covered. Thank you, and have a good lunch and good.